Hiya both. New term, new topic. We are continuing on with the Unit 4 syllabus at pace. By this rate, we'll be about halfway through by the time we get to the end of the year. Obviously, we'll have to go over it all in September, but we're in a lot further on already than we would be normally because of what's happened. So let's press our advantage now and move on to this new topic of polar coordinates. I'll get your Maclaurin's expansion assessments back to you later today, so you can have a look at them and make sure everything's all right there. Right, Mrs. Fran's going to start taking on the differential equation stuff now. She's back with us, so she's going to be setting you lessons on that from now on. So polar coordinates then. What on earth are polar coordinates? Well, it's a very simple idea. If I have a point in space, the origin, and I want to reference another point in space, traditionally what I would have done, or what we would have done in school, is we would have had an x-axis and a y-axis, and the point would be referenced by, say it's here, by referring to the distance along the x-axis and the distance up the y-axis, and we would call that the point x, y. Nothing wrong with that, very useful. We can describe sets of points by setting up relationships between y and x. For example, the relationship y equals x squared, as you know, is this set of points around here like that. Okay, and you can have anything. These are ways of coming up with a subset of points in the whole space that fit a relationship. Nothing new there. Okay. So what if I wanted to refer to this point here, but describe it in a completely different way? There may be some advantages in doing that in certain situations. Well, one way of describing this point, let's call it P, is not to think about how far along the x-axis you go and how far up the y-axis you go to get to the point from the origin, but how far from the origin you go and in what direction. In other words, I'm interested in how long that line is there, let's call it R, and on what angle or direction I travel compared to a defined direction, if you like. The defined direction is the positive x-axis. So I'm going to say that if I'm going in this direction, the angle I'm traveling on is 0 degrees or 0 radians. Okay, therefore I can now talk about the angle I am traveling on to get to my point as the angle between the reference direction, we're going to discover later that's called the initial line, and the direction I want to travel in. So let's call that theta, and I'm now in a position to talk about this point here not just as the point x, y, but as the point r, theta. If I know the value of r and I know the value of theta, I know where I am in space relative to the origin. And every point in space has a unique value of r and theta. And that's how it works. Very, very simple. Now here's the fun thing. If you know the coordinates of a point in terms of x and y, you also know the coordinates of the point in terms of r and theta. You just need to know how to go from one to the other. So for example, if x, y was the point 2, 1, say, all right, so that's the Cartesian coordinates of the point P. I can easily, I'll show you how to do it now, change that into polar coordinates by doing some sort of calculations on the values 2 and 1. How do we do that then? Well, it's really, really simple. Let's look at our diagram and let's actually put those values of 2 and 1 on the diagram. Well, that would be 2 and that would be 1 up there, and there'd be a right angle here, and then using a little bit of simple Pythagoras and trigonometry, I can easily discover the values of theta and r. Let's start with r. Well, r is a hypotenuse of a right angle triangle, so I know that r is equal to the square root of 1 squared plus 2 squared. which is going to be the square root of 5. So that distance there is the square root of 5. And the value of theta is simply going to be 10 to the minus 1 of a half. And I'm going to need my calculator for that because I don't know what that is. Okay, I could be in I'm in degrees, so I'll do it in degrees. Sometimes it's done in degrees, sometimes done in radians, depending on the question. This is in degrees. There we are, 26.6 degrees. So, my point P, which is at the point 2, 1, if you're referencing it using Cartesian, could just as easily be described as root 5, 26.6 degrees. Okay, so that is the polar coordinate equivalent of the point 2, 1. And like I say, every point in space could be defined using this system. Usually we reference the angle from minus 180 to 180 rather than 0 to 360. So all the angles around here would be 0 to 180, and the angles around here would be would go around to minus 180. So we start at minus 180 here, around to 0, and then back round to 180. Okay, that's normally the standard for polar coordinates. And obviously, if it was in terms of radians, it would be from minus pi to pi. Okay, so what about if I had a point that's already in polar coordinates and I wanted to change it back into Cartesian? So say, for example, I've got a point here that is on an angle, so we say the angle here is, I don't know, 30 degrees, and the length of this line here is 4. So let's call this point Q, and I want to change that back into Cartesian equation coordinates. Oh, I'm taking a lot of sense here, aren't I? Well, that's really easy as well, and it's really easy because I can easily go from r and theta back to x and y. Let me draw a new diagram to show you this. Again, from looking at the triangle. I'll do it in the first quadrant because it's easier to understand, but the rule applies whatever quadrant you're in. So if I've got this point here, and I know that it's r away from the origin, and it's on an angle of theta, what I'm looking for is a way of describing these two values here, because they would be the x and the y coordinate. So if that's x and that's y, this is a right angle triangle. I can clearly see that from Pythagoras that sine theta is opposite over hypotenuse, so that would be y over x. Y over r, get it right. And if I rearrange that, I'll end up with y equaling r sine theta. Okay, and a similar trick with cos theta. Cos theta is adjacent over hypotenuse. Rearrange, I'll get x is equal to r cos theta. Okay, so those two equations there will allow me, if I know r and theta, to come up with an x and a y coordinate. Really, really simple. So for my coordinate q here, which has 4, 30 degrees as its polar form, to change it into Cartesian, I just go y equals 4 sine 30 and x equals 4 cos 30. Or sine, oh, I've gone wrong, it's not 30. Sorry. Oh, dear me. Can you see my mistake? Not 30 degrees. Because, remember what I said about the angle? It's described from the positive x-axis, so it's actually 120 degrees. And now I'm going to have to wait for my Tipp-Ex to dry before I can fill those in. So I will carry on with my Tipp-Ex drying and actually work them out. So it's 4 times sine of 120. This is the y coordinate, which is 2 root 3. And then the x is 4 times cos of 120, which is minus 2. So this coordinate here is actually the Cartesian coordinate minus 2, comma 2 root 3. Oh dear. Just wait now for it to dry. 120. Oh God. Try a biro. 120, 120. There we go. That'll do. And that's how you do it. That's how you change from polar to Cartesian, that one, and Cartesian to polar, which is that one. So if you now read the notes on integral maths and attempt the first exercise, you should be able to have a fair old stab at it. Oh, one more thing. I want to talk to you a little bit about functions, because this is all very well being able to change from one coordinate to another. Where it gets a bit more exciting is when you're actually defining curves in the same way as we define y equals x squared. So, I mean, on that, for example, it's possible to change that into a Cartesian, into a polar version, simply by subbing in for y and x. So if I take these things here, I can sub them in. So I'll have r sine theta equals r squared cos squared theta, like that. Okay, and if I rearrange that to make r the subject, so I mean, I shouldn't really do this. I'm going to cancel an r out from both sides. That's not strictly the best way of doing this, but I will do it there just for the convenience. I'll have r equals sine theta over cos squared theta, which is oh god, the same as sine over cos is tan, 1 over cos is sec, so that's the same as r equals tan theta sec theta. Now, if I were to plot that on a, so choose different values of theta and plot it, I should end up with y equals x squared. Shall we do it? Okay, so this is polar coordinate paper, and so I'll do it here. R equals tan. If I had Desmos, I could just type it in and you'd see. But I'll do it old school. R equals tan theta sec theta. Watch this. Bang, calculator. I shall do it using table mode, so I don't have to do them all individually. If I go into table mode and I type in for different values of theta, tan theta sec theta. So I'm going to go tan x sec. No, I can't do sec on here, so I'll just have to do or divide it by cos theta, which is the same as sec theta. Like that. It's better work now. Right, so if I start at 0 and go round to 180 in steps of 15, please work. Okay. So, first problem I've got is my scale here isn't very good for doing this, but so what I will do is I will actually pretend that I was plotting 5 tan theta sec theta rather than tan theta sec theta, just so the scaling works a bit better. So what I'll need to do now is to times all of that by 5. So if I go back to there and just put 5 times in front like that, that should work. Right, that's better. Okay, so now to plot these points. So remember, these are the angles, and these are the distance out I need to come on that angle. So first one 0, 0. Well, that makes sense because y equals x squared starts in the middle. The next one 15, 1.387. So this is only rough. So that's about there. And then the next one is 30 degrees and it's 3.33. So it's around about there. 45 is there and it's 7 out. So 7 is there and it's just over 7. So it's there. And these are going to get bigger now. 17 out. Right, that's for 60 degrees. So I'm kind of, oh, I'm right. I'm almost off the top of my page. I'll go there and I'll just join that up. Okay, once I get past 90 degrees, you should see 105 is up here. And if I keep going, 120 will be the 7. Sorry, that wasn't 105, that was 100. And 20 was 17. 130, I think you get the idea. 135 is 7, there. 150 is 3, which is 1, 2, 3, there. Do you get the idea? And 165 is 1 and a bit, which is there. And if I join that up, you get y equals x squared. Boom! So you can represent polar coordinate functions that look like that in terms of polar. Just try the exercise and let me know what you think. Okay, bye for now.